March 4, 1944, Berlin. For the first time in history, American bombers are striking the heart of Nazi Germany with full fighter escort for the entire mission. Hermann Göring, commander of the Luftwaffe, watches in disbelief as hundreds of silver P-51 Mustangs dance through the sky at 30,000 feet, shredding his best fighters to pieces. "When I saw Mustangs over Berlin," Göring would later say, "I knew the jig was up." But here's what Göring didn't know. What he was really looking at wasn't just American engineering. The planes tearing apart his air force were powered by an engine that wouldn't exist without a British metallurgist nobody's ever heard of. A man who solved a problem everyone said was impossible. A man who created an alloy that was literally forbidden by the laws of science as they understood them. His name was Leonard Bessemer Feil. And the material he invented in 1941 didn't just change one war, it changed the entire future of flight. This is the story of how metal won World War II. Let's rewind to 1940. Britain is standing alone against Nazi Germany. The Luftwaffe is bombing London every single night, and the Royal Air Force is desperately trying to figure out how to fight back. They had great planes. The Spitfire, the Hurricane, beautiful machines, but they had one massive problem. They couldn't fly high enough, fast enough, for long enough. The issue wasn't the airframe. It was the heart, the engine. See, at 10,000 feet, the air has about 70% of the oxygen it has at sea level. At 20,000 feet, 50%. At 30,000 feet, where the real fighting happened, there's barely 30% of the oxygen. And internal combustion engines? They're basically controlled explosions that need oxygen to work. No oxygen equals no power equals dead pilot. The solution was something called a supercharger, basically a turbine that forces more air into the engine. Think of it like this. If your engine is drowning in thin air at high altitude, the supercharger is the lifeguard forcing oxygen down its throat. But here's where it gets interesting. In 1940, Britain's best engine, the Rolls-Royce Merlin, had a single-stage supercharger. It worked okay up to about 15,000 feet. After that, performance fell off a cliff. The Germans, meanwhile, were already working on high-altitude interceptors. The British needed to leap ahead. The answer? A two-stage supercharger. Two turbines in series, spinning at ungodly speeds, compressing air twice before feeding it to the engine. The first stage does the initial compression. The second stage takes that already compressed air and compresses it again. In between, an intercooler cools the air down so you can pack even more of it into the cylinders. On paper, it was brilliant. The Merlin 60 series engine with this two-stage setup would produce over 1,800 horsepower and maintain that power all the way up to 30,000 feet. That's a 300 horsepower gain over the older Merlin at high altitude. That's the difference between life and death. There was just one tiny problem. The supercharger impellers, the turbine wheels spinning inside these things, were experiencing conditions that would make hell look like a vacation. They were spinning at 25,000 revolutions per minute. The blade tips were moving faster than the speed of sound. And the temperatures? We're talking 850 degrees Celsius. That's hot enough to make steel glow cherry red. Hot enough to make most metals turn into pudding. The centrifugal forces alone were enough to rip conventional blades apart. Add in that heat and you had a recipe for catastrophic failure. Blades would stretch, warp, snap. And when a supercharger blade lets go at 25,000 RPM, the entire engine becomes a grenade. British engineers tried everything. Specialized steels, chrome molybdenum alloys. Every material they threw at the problem failed within hours. Some materials could handle the heat but couldn't handle the stress. Others could handle the stress but melted. They needed something that could handle both simultaneously. And according to the Metallurgy of 1940, that material didn't exist. Enter Leonard Bessemer Feil. Born in London on March 13, 1898, Leonard had metallurgy in his blood. That middle name, Bessemer, wasn't random. It was a tribute to Henry Bessemer, the inventor of the Bessemer steel-making process that revolutionized the Industrial Revolution. No family relation, but the name was a reminder of what metallurgists could achieve when they thought differently. Leonard was a brilliant student, loved chemistry, had a face like an angel and a mind like a calculator. By 1940, he was working as head of research at Mond Nickel Company, which was part of the International Nickel Company, NCO. Mond operated the Wigan Works in Birmingham and Hereford, England. These facilities specialized in exotic nickel alloys, and Leonard Fiel was their wizard. Now, nickel alloys weren't new. Nickel-chromium alloys, basically stainless steel's tougher cousins, had been around since before World War I. They were corrosion-resistant and could handle reasonable temperatures, but nobody had really pushed them to their absolute limits. When the Whittle jet engine program came knocking in early 1940, asking for materials that could survive inside a jet turbine, Fiel saw an opportunity. Jet engines were even more extreme than superchargers. Turbine blades in a jet engine face temperatures exceeding 1,000 degrees Celsius and rotational speeds that create stresses measured in tons per square inch. The problem was understanding why metals failed under these conditions. It wasn't just strength. It was something called creep resistance. Creep is when a metal under constant stress and high temperature slowly deforms over time. Imagine pulling taffy. At room temperature, taffy is hard. Heated up, and under even light pressure, it starts to stretch. That's creep. Turbine blades and supercharger impellers were experiencing creep in real time during operation. The blades would slowly elongate, millimeter by millimeter, until they rubbed against the housing or lost their aerodynamic shape. Either way, catastrophic failure. Fiel realized that to solve this, he needed to do something counterintuitive. Conventional wisdom said, you strengthened metals by making a solid solution, dissolving alloying elements uniformly throughout the base metal. But Fiel wondered, what if you intentionally created tiny precipitates, microscopic particles of a second phase, distributed throughout the metal? These particles could act like anchors, physically pinning the crystal structure in place, preventing the atomic level sliding that caused creep. In 1941, working in the laboratories at the Wigan Works in Hereford, Leonard Fiel began his experiments. His base was nickel, about 60%. Nickel has a face-centered cubic crystal structure that's stable at high temperatures. That's your foundation. Next, chromium, about 20%. Chromium forms a protective oxide layer that prevents the metal from corroding or oxidizing at high temperatures. Basically, it creates an invisible shield. But here's where it gets clever. Fiel added titanium, about 2%, and a small amount of aluminum, less than 1.5%. Now, at room temperature, these elements dissolve into the nickel-chromium matrix. But at elevated temperatures, under the right heat treatment, they form a specific compound, nickel-3 titanium aluminum. The formula is Ni3, Al-Ti. This compound forms as submicroscopic particles, gamma-prime precipitates, throughout the alloy. They're so small you can't see them without an electron microscope. But they're everywhere, billions of them. And they have a special property. They don't weaken with temperature. In fact, they actually get stronger up to a certain point. These gamma-prime precipitates lock the crystal structure in place. When stress tries to make atoms slide past each other, creating creep, these particles block the path. It's like trying to slide furniture across a floor covered in ball bearings versus one covered in sandpaper. The precipitates are the sandpaper. Fiel called his creation Mnemonic 75 initially, but quickly realized he could optimize it. By adjusting the ratios and adding trace amounts of carbon and other elements, he developed Mnemonic 80. This version had even better creep resistance and could maintain its strength up to 950 degrees Celsius. Testing began immediately. Sample blades were machined, heat-treated, and subjected to brutal conditions. Spinning test rigs, furnaces that simulated combat temperatures, stress tests that would make a medieval torturer jealous. And the results? Mnemonic 80 didn't just survive. It thrived. Where other materials would fail in hours, Mnemonic 80 ran for hundreds of hours with minimal degradation. The gamma-prime precipitation hardening was working exactly as predicted. But there was a catch. Mnemonic 80 was incredibly difficult to machine. The same properties that made it strong made it resistant to cutting tools. It would wear out drill bits and milling cutters at an alarming rate. Manufacturing turbine blades from this material required specialized tooling, careful speed control, and enormous patience. And there was another problem. Nickel was a strategic material. Britain was importing most of its nickel from Canada, and shipping lanes were under constant attack from German U-boats. Every kilogram of nickel that went into supercharger blades was a kilogram that couldn't go into armor plate, shell casings, or electrical components. Using this alloy wasn't just an engineering decision, it was a strategic gamble. The British government essentially had to decide, do we bet precious nickel resources on an unproven alloy for an unproven engine concept? In 1941, with Britain's back against the wall, they made the call. Yes. Production of Mnemonic 80 began in earnest. Henry Wigan and Company's Hereford facility went into overdrive. Ingots were cast, forged, and heat-treated. Impeller blades for the new Merlin 60 series engines started rolling out. Each blade was inspected, tested, and certified before installation, and then came the moment of truth. By late 1942, the first Merlin 60 series engines with two-stage superchargers and Mnemonic 80 impellers were entering service. They were initially fitted to high-altitude variants of the Spitfire and Wellington bombers. The performance increase was staggering. Spitfires that could barely fight effectively above 25,000 feet were now dominating at 35,000. Pilots reported that the engine felt like it had no ceiling. Power just kept coming, even as the air got thinner and thinner. But the real game-changer was about to happen across the Atlantic, the North American P-51. Mustang had been designed in 1940 as a fighter for the British Royal Air Force. It had a beautiful laminar flow, wing design that gave it exceptional speed and range. But there was a problem. It was powered by an Allison V1710 engine with a single-stage supercharger. At low altitude, the Mustang was phenomenal. But above 15,000 feet, it was a dog. Slow, sluggish, useless for high-altitude bomber escort. Then someone had an idea. What if we put a Merlin engine in the Mustang? In October 1942, a British test pilot named Ronald Harker flew a Mustang and immediately recognized its potential. He suggested replacing the Allison engine with a Merlin. Rolls-Royce agreed to try it. They pulled a Mustang airframe, stuffed a Merlin 61 with the two-stage supercharger into it, and fired it up. The first flight was in October 1942, and it was immediately obvious they had created something special. The Merlin-powered Mustang, designated the P-51B in America, could cruise at 440 miles per hour at 30,000 feet. It had a combat radius of over 750 miles with drop tanks. That meant it could fly from England, escort bombers all the way to Berlin, fight German interceptors over the target, escort the bombers back, and still land with fuel to spare. No Allied fighter had ever done that before, not even close. And at the heart of this transformation were those Mnemonic 80 impeller blades, spinning at 25,000 RPM, forcing oxygen into the Merlin cylinders at altitudes where the air was thinner than the top of Mount Everest. Production ramped up insanely fast. North American Aviation in California and Texas started building P-51s by the thousands. Packard Motor Company in Detroit began producing Merlin engines under license, designated the V1650. By early 1944, hundreds of P-51 Mustangs were pouring into England every month. The impact on the air war was immediate and devastating. Before the P-51B arrived in numbers, American bomber losses over Germany were catastrophic. The 8th Air Force was losing so many B-17s and B-24s that crew survival rates were terrifyingly low. Missions to deep targets like Schweinfurt and Regensburg in August and October 1943 saw loss rates of 15 to 20%. Do the math. Fly 5 missions and statistically, you're dead. The problem was simple: P-47, Thunderbolts, and P-38. Lightnings could escort partway, but they didn't have the range to go all the way. That left a gap over Germany where bombers were on their own, and the Luftwaffe exploited that gap ruthlessly. Bf-109s and Fw-190s would assemble in huge formations and tear into the bomber streams like wolves into sheep. Then in February 1944, everything changed. The P-51B Mustangs arrived in force. Operation Argument, also called Big Week, was a coordinated series of massive raids against German aircraft production facilities. For the first time, the bombers had fighter escort all the way to the target and back. And the Mustangs didn't just escort, they hunted. The P-51's combination of speed, altitude performance, range, and maneuverability made it superior to almost every German fighter it encountered. At high altitude, where the 2-stage Merlin with its mnemonic impellers thrived, the Mustang could outclimb, outturn, and outrun the Bf-109G and Fw-190A. German pilots were stunned. They'd grown accustomed to American fighters turning back before reaching Germany. Now they were being attacked over their own airfields. The Mustangs would drop their external tanks, accelerate to combat speed, and engage with energy to spare. The Luftwaffe's numerical and tactical advantage evaporated almost overnight. The statistics are staggering. During Big Week in February 1944, the 8th Air Force flew over 3,800 bomber sorties. Losses were still significant, but the Luftwaffe lost over 600 fighters. German pilot losses were even worse because experienced pilots were irreplaceable. By March 1944, when the first full-scale mission to Berlin was flown on March 4th, the psychological impact was crushing. Berlin, the capital of the Third Reich, was being bombed in daylight with American fighters circling overhead. Göring's promise that no Allied bomber would ever reach Berlin was exposed as a lie. The P-51 Mustang's combat record in Europe is one of the most lopsided in military history. Mustang pilots claimed 4,150 enemy aircraft destroyed in air-to-air combat during World War II. The kill ratio was approximately 11 to 1. For every Mustang lost in air combat, 11 German aircraft went down. That's not a battle. That's a slaughter, and it broke the Luftwaffe. By D-Day in June 1944, German air superiority over France was gone. By the fall of 1944, the Luftwaffe was a shadow of itself. They had planes, but they'd run out of experienced pilots. And without experienced pilots, the planes were just metal coffins. The combined bomber offensive, the strategic bombing campaign against Germany, succeeded because of one plane. The P-51 Mustang, powered by one engine. The Rolls-Royce Merlin, enabled by one alloy. Mnemonic 80, created by one man. Leonard Bessemer Pfeil. So what happened to Leonard Pfeil? He continued his work throughout the war, developing improved versions of the mnemonic family. Mnemonic 80A in 1945 was even stronger. Mnemonic 90 followed. Then Mnemonic 100, 105, and 115. Each generation pushed the temperature limits higher. After the war, these alloys became the foundation of the entire jet age. The same material science that enabled the Merlin's supercharger enabled the first practical jet engines. British jets like the Rolls-Royce Nene and Derwent, American jets like the J-47 and J-57, they all used turbine blades made from mnemonic alloys or their descendants. Commercial aviation, spaceflight, modern gas turbines for power generation. They all trace their lineage back to that laboratory in Hereford in 1941 where a metallurgist figured out how to make metal stronger by making it more complicated. Leonard File was elected a Fellow of the Royal Society in 1958. He received the Institution of Metallurgists Platinum Medal. He died in 1969, largely unknown to the public, but revered by every materials scientist who understands what he achieved. Today, the descendants of mnemonic 80, superalloys like Inconel, and advanced single-crystal turbine blades allow jet engines to run at temperatures exceeding 1,500 degrees Celsius. The turbine inlet temperature of a modern fighter jet engine is hotter than the melting point of the turbine blades themselves. The only reason they don't melt is because of internal cooling channels and thermal barrier coatings built on the same principles Fiel pioneered. Control the microstructure, control the properties. So the next time you see a jet engine, remember, it exists because one man in 1941 looked at an impossible problem and decided the laws of metallurgy just needed better laws. And because of him, the P-51 Mustang went from a decent low-altitude fighter to the plane that won the war. That's the power of materials science. One alloy, one engine, one plane, change the world.